Okay, so this is a type of question showing a little bit more complicated calculation. So fewer words, but more of a calculation going on here. It's worth 5 marks, so there's a bit more required than you would expect. So figure 2 shows the apparatus a student used to measure the force acting on a conducting wire in a magnetic field. The wire is clamped to stop it moving. So we've got a permanent magnet sitting on top of a balance, and you've got a wire here which can't move, but will then have a current placed through it. The current will run in this direction here, and what will happen is this will produce its own magnetic field and force the top of the balance downwards and give a reading of the mass in grams, or as it says here, in milligrams. Now, what they would like us to calculate in the end is the length of the wire in the magnetic field. Okay, so let's start thinking about the things that we know. We're given the current in the wire, the balance reading in grams, the magnetic flux density, and the gravitational field strength. So I think I'll just put the symbols down there. So current, I, balance reading is going to be mass, magnetic flux density is going to be B, and gravitational field strength, well I know that is little g. And I'm just going to write these out because I'm a bit concerned about the units being used there, because I don't like grams. I much prefer that to be in kilograms. So I've got 0.4 of a gram, so that's 0.00. So what's that? That's hundreds, tens, ones, 4 kilograms. Okay. Times that by 1,000. 1, 2, 3. Yes, that's correct. This is 0.03 Teslas, and this is 9.8 newtons per kilogram. All right. What else do we need? So what else do we know? Well, actually we do know that something's going to relate BI, and we need to know L. So we know that the force is equal to BIL. Okay. So we've got B, we've got I, we want L, we haven't got the force, but we have got the mass and the gravitational field strength. And we know that the weight is equal to mg, and this weight is going to be the force measured on this meter. So I can actually say that mg is equal to BIL. Okay, so I think we have everything there. Let's just check the question. The student changed the current in the wire and recorded the new balance reading. The table shows all the data recorded by the student, and there it is. Calculate the length of the wire in the magnetic field. All right, let's have a go at that then. So we're going to start with force. Force equals to the weight, which is equal to mg, and that's going to be equal to 0.0004 times 9.8, which equals, reaching for a calculator, so that equals 0.0004 times 9.8 equals 0.00392 newtons. Keep all your significant figures at this stage, round off at the end. But we also know that F equals BIL, so let's substitute in here. So 0.00392 equals magnetic flux density 0.030 times by the current 2.2 times by the length, which we don't know. So let's rearrange for length. 0.00392 divided by 0.030 times 2.2, and let's pop that into the calculator. and I get a length of 0.0594 meters. So that's your final answer. Now everything's given here to two significant figures, so let's put that in there. 9 meters. Now, last thing you need to do is check, is it reasonable? Well, that is, how is that? 5.9 centimeters. That's pretty decent. That's a reasonable number for the size of the magnet and the size of the balance. So we'll take that as the answer. Done.